Hello, everyone, and welcome. Thanks for coming. If you could just, find a seat, get some food, get some beverages over in the corner, and we'll get started. My name is Tim Dempsey. I'm here on behalf of the Somerset County Business Partnership, which is it's basically our Somerset County Chamber of Commerce and more, as they say. Has about 700 businesses. I do environmental consulting, cleanup of contaminated sites. I was here yesterday on a green jobs panel, which was awesome. May have seen some of you there. Before I introduce today's speakers, I wanted to first introduce Nadine from the Citizens Climate Lobby. She would like to say a few words.
Good afternoon, everybody. Good morning. Oh, we're still morning. I'm Nadine Cadell-Sapperman from the local chapter of the Citizens Climate Lobby. I want to thank Raritan Valley Community College for allowing us to have a demonstration today. And actually through this week, we are singularly focused on putting a price on carbon. So if you care about climate change and it's an issue that you want to learn more about or you want to know about a solution so that we don't get bogged down in the, oh my gosh, what's going to happen, but how can we do something about it, I would encourage you to come over to our table. We are encouraging people to sign a letter. If you haven't yet signed one of these, we are collecting them and we're going to be delivering them to your member of Congress when we meet with them in June. So if you want to have your voice heard, saying you care about climate change and you want our federal government to do something about it, this is your opportunity. So we'll be in the back table. We do have meetings monthly. I can tell you more about that, but our big action today is to get you to think a little bit about climate change and fill out one of these letters for us so we can take it to your member of Congress and have your voice be heard. Thanks so much.
Thank you, Nadine. I should be a little more specific. So I'm with the Sustainable Somerset committee of the Somerset County Business Partnership, and we get together every month, and we are made up of business leaders throughout the community who pursue growth and profitability through sustainable practices that could contribute to the well-being of the overall community. And through the services of the business partnership, members enjoy the reduced expenses and increased profitability from initiatives that we set out, such as a green challenge, which is an inventory and questionnaire and program that businesses can enroll in to get them thinking more about how their business can become more sustainable. And we also have networking events and access to we provide access to green vendors who provide those sustainable services such as energy audits, solar paneling, environmental consulting. But anyway, I'm here today to introduce our speakers who are Monika Parkitna and Chris Kellogg. They're both architects. I'll introduce them both at the same time, then they're going to do a handoff between each other and show you some of these cool features that are up here. Monika had her BA of Architecture from NJIT right here in New Jersey in 1996. So she's been studying in New York and New Jersey, or practicing in New York and New Jersey since then. She's a registered architect in the state of New Jersey. She's a lead accredited professional with the Green Building Council. Previously in New York, she was with Lineworks, Alfredo DeVito Architects, Gene Kaufman Architect, and STV Incorporated. During her tenure years, Mrs. Parkitna was involved in the design, production, and coordination of commercial, educational, and retail projects. In recent years, she's devoted her time to residential projects. Her work includes multiple renovations and additions, such as ADA House. It was an addition and a remodel to accommodate a wheelchair-bound client. And she recently completed high-energy performance housing, which was presented, or as a home, that was presented during the 2015 New York Passive House Days. And Chris Kellogg, he's been in the practice for 30 years. He has his own practice, and with 30 years as an architect, Kristen Kellogg started Steel Kellogg in 2007 in response to environmental concerns. As a student, he took a keen interest in sustainable design, which he's maintained through the years. He offers a breadth of experience from disaster assessment specialist, and he's worked on hospital campuses, clinics, high-rise office, corporate interiors, multifamily, and single-family residences. He has his Master's of Science in Architectural Studies from the University of Texas, Master in Design Studies from Harvard University, BA in Architecture from Boston Architectural Center, and even a French Architectural Study degree at the University of Nantes in France. So, ladies and gentlemen, give a round of applause for Chris and Monika. I think Chris is going to start. Chris is going to start, and then he'll do a handoff to Monika.
Hello. Okay. So as you can see, we have a lot of stuff to show you today, both on the screen and in the flesh. So we'll get started. Basically, we're showing you two houses, one done under one certification system and one done under the other. And then I brought a third house that's kind of related to both of those just for a side discussion. So as you will see, these homes are quite different in appearance. What connects them is a significant reduction in energy use. The average New Jersey home of 2,400 square feet spends over $3,000 on energy every year. New Jersey is what we call a heating-dominated climate, so a lot of that $3,000 goes to heating. The United States is broken into climate zones, so you have a variety of zones throughout the United States that have different requirements. Some are cooling-dominated, which we imagine would be Florida, Texas. So in this climate zone, we're looking at two houses. And what you'll see, and I haven't actually had this definitively confirmed by Monika, but your house runs on $0, right? Almost. Yeah. My house runs on $0, and the other house we're going to show you is also running essentially on $0. So the thing is, with running buildings that allegedly cost nothing to run, there's all kinds of ways to figure that. And some people would say, well, it's not really true. You're not really running for free because you got incentives and you got other, factors. So it's a very complex thing to actually try to tell people that you're running a building for nothing. There's so many factors that go into it, including your climate zone, who the occupants are, that particular year. There's a lot of variables. But I think what's critical is that what Monika and I have done is to take buildings that cost, on average, $3,000 a year and up, because her home is more like the size of an average New Jersey home. My home is about twice the size, so my annual cost, if it was a conventional home, could be $6,000. So we're both running our homes at about zero. It's important to understand that every building, with all of its internal systems, its insulation, its windows, its orientation to the site, and the occupants that occupy it, that all sets up this huge variability in the final net result. So, as a quick overview, you probably know or suspect that the United States is one of the leading energy hogs in the world. We represent 7% of the world population. We consume 30% of the energy of the world. In the United States, there's a particular, for Monika and for me, there's a very critical element that takes almost half of the total energy use that's used in the United States is for buildings. 40% is the operation of the buildings, 10% is roughly what the buildings need to generate to build them, demolish them, and all the construction activities that go on to transfer materials, to take stuff to the dump. That's about another 10%. So we're in the range of half of the US energy consumption just due to buildings. So that inspires architects to really get on the plate here and make something happen in such a large sector of our energy pie. So what Monika and I are going to show you today are a variety of ways to reduce the overall energy consumption. So how did we achieve it in our two different projects? Monika will talk about hers, She worked under a certification system called Passive House, and I worked under one called LEED. These are systems of analyzing and certifying buildings that they are performing at or better than standard code. So one of the areas that we look at is tightness. A building has to be tight to be efficient, and many of your homes may be really inefficient. In fact, 40% of the energy expended in a typical home is lost just because you have leaks, what we call infiltration. So the air gets into the house through the chimneys, through the cracks around the windows, through the floors, all kinds of various ways that there's a transfer between the outside and the inside. And that can, in some cases, be as high as 40% of the total energy expense. We tighten buildings up to make them more energy efficient, and then we do something called a blower door test, where we take the central door of the house, we seal the house up nice and tight, and then we run a fan and we create a negative pressure on the interior of the home. And then we can go around. I have a very precise device here, the top of my head allows me to feel drafts. So I can walk around and tell if I've got a draft dropping in somewhere. So when the fan is blowing, we then go around the whole house and we verify that there aren't any leaks. Now we do this before it's insulated and before it's finished, because otherwise you couldn't find the leaks, or if you could, you couldn't get to them. So we go around carefully at every joint, top to bottom, up and down, to make sure the house is tight. And there's a measure called the air exchange. So we're looking for the lowest air exchange possible. In Monika's case, she'll talk to you about the air exchange required for a passive house. There was not a specific target for the LEED system that was certified for my house here. This model is of that house. But ours is quite low. I'm sure it's not as low. I've forgotten what Monika's is, but I think mine's not as low as hers. Then because you've tightened the house up, you have to then provide controlled ventilation, because you'll really get very ill in a building that has no air in it. So we then have to introduce exchange systems. And one of the most common types is called an energy recovery ventilator, or ERV. And it's a very simple little device, runs very efficiently on a little highly efficient ECM motor, and basically gives you fresh air into the home. And one of the ironies about American building codes is that there really has not been much ventilation required in typical individual homes. You know, if you have a bathroom with a window, you don't even have to have a fan in the bathroom. All you have to do is open the window. That's the code. Now it's beginning to change, because as we tighten up our homes, we're realizing that we're not only having a lack of oxygen, but we're also beginning to not live healthily, because all of the outgassing of the materials in the house. So that's another thing that the LEED system looks at versus the passive house system. Let me just distinguish those two systems briefly. The LEED system is a certification for sustainable buildings, but it goes much broader than the passive house, which is really about energy consumption. The LEED system looks at the interior materials, because they want your interior to be healthy. So we look at furniture, fabrics, carpeting, glues. All of that stuff is loaded with fire retardants, formaldehydes, and other chemicals. So we need to make sure that your home is healthy. And one way we do that is, because we can't control every substance that goes into your home, we then provide the ERV that I mentioned earlier that will then exchange the air in the home on a regular basis. The other factor that the LEED people also look at is durability of materials. They want to make sure you build a building really well so that it lasts longer than the average American house, which right now the average American house is somewhere around 35 years, the age of the house. In some states, like New York, it's higher for some reason. It's like 50 years is an average age of the house. But we replace them pretty often, and one of the reasons we replace them is because they just wear out. They're junky, they fall apart, they're not built as well as they should have been. Another thing that we need to talk about, and Monika will talk about in detail on her house, is the building envelope. So what I was just going through is listing the various ways we try to keep the energy low and how we got to $0 on our annual expense. So you need to take the building envelope and make it tight, as we mentioned earlier, but you also got to insulate it really well. So we provide a much higher level of insulation than a typical house would have. But secondly, we also wrap the house if we can. And that's one of the key and most common new ways now of insulating a building, whether it's commercial, whether it's this building or my home. You want to wrap the building. It's like the winter coat. You go out in the winter, and you have a little stick that goes from the surface of your North Face coat all the way to your skin. And if I scale the house down to the scale of your body, you might have a little stick running up down the whole length of your body, maybe every 1.5 or 2 inches. Going all around your body, you'd have this little stick, and that's called a thermal bridge. That's allowing heat to escape through that structural element out to the exterior. Most all the homes you guys live in, including all of these college buildings, have got numerous thermal bridges connecting the inside to the outside. They're insulated between the bridges, but a stud or any kind of blocking or pipe that goes through the wall is a thermal bridge. So what we try to do is take those thermal bridges and eliminate them as much as possible. You can't always get rid of all of them, but they're a huge source of heat loss for a building. We also have to deal with doors and windows. Now, when you renovate an existing house, it's a little more expensive to get into replacing windows because you inevitably have to mess with the interior finishes or the exterior siding or the trim work. When you build a new building, whether it's commercial or residential, if you don't use high-performance windows, you're either violating code or you're just crazy because you can save a fortune with properly specified windows that can double the R value, the resistance to heat loss with a window or a door. And then lastly, I just mentioned the other thing that's critical to the building itself for energy efficiency are the equipment that you select. If you are a typical HVAC contractor, you often oversize equipment because you think bigger is better. The problem with oversizing is that the system then runs what they call short cycling, so it runs a lot. It runs, meets its need, immediately stops, runs again, stops. Very inefficient, you lose energy. You need a system that's sized to the house and to the insulation levels you've provided. So that's another piece of the puzzle that you have to put into the mix. And this may all sound fairly complex, but it's not, because you have people out there like Monika and like me, you have energy raters, you have building codes now. So a lot of this is really being spoken to. It's out there. It's in the lumber yards. You can go to Jaeger Lumber or any other lumber yard, and they can talk to you about the energy efficiency of windows and doors and insulation products. So it's not new anymore. I mean, it's new. We're only a small percentage of what the total American housing stock is doing the kind of work we're doing, but still, it's out there, so don't despair. So I'm just gonna run through my house very quickly. I'll show you some images. So this is this morning. Just, I don't know if it snowed here, but we had to dig out the driveway just to get here. That's the back of the house, so that's my north side. My house is turned to face perfect solar south, this way. What we discovered is that the oldest house in Madison, built in 1730, is on the same angle as our house. And I discovered that later when I looked at the maps of the neighborhood. It's just up the hill from our house. Up here, the old farmers, they knew where to find heat. We've completely forgotten that the sun is the perfect source for heat. So they also oriented their barns to face south. And you can still see that up in dairy country all throughout New England, even in New Jersey, that the barns are oriented, if they know what they're doing, to face south, so the cows have a little extra warmth. So this is the north side of the house. This is the west-facing front entrance, so you can see the big overhangs we have around some of the elements, and they help control the solar. This is a view of the back of the house. This is a view that gives you a little oversense of the whole spread of it. This is from the schoolyard across the street. So you can see up on the main pitched roof, we have photovoltaic collectors. Down below, that element sticking up there over to the right is a solar hot water collector. And there's more collectors on the lower wing sticking out this way. Then the big overhangs help me to control the sun. So the windows that are low down in the first level facing this way, that's the living space, and then that's the master bedroom. Those have special glazing on them that allows extra heat to get in. So that's a trick you can do with high performance glazing, is you can actually, oh, there's a pointer, okay, I think I'm fine. You can actually control how much heat you get or don't get just by putting different chemicals on the coating of the glass. And in this case, we've got triple glazing. I'll show you a sample. So you can actually, what the Canadians call, you can tune the glazing. So here's a triple glazed unit, and you guys should all come up here afterwards and you can look at all these samples we have. But 3 layers of glass. twice the R value, twice the insulation value of a conventional double unit. But then you can add coatings on the inner surfaces of this glazing. And in this case, I added special coatings on those two there to let the heat come in. Now, unfortunately, when double glazed windows were invented, it was also at the same time Americans were moving big time down to Tennessee, Atlanta, and out in Southwest Texas. So guess what kind of windows they wanted? They wanted windows that would let the heat in, because we have a cooling dominated climate down there. So all the insulating units that are out there pretty much still today on the market, go into Jaeger lumber, buy the window, keep the heat out. And from our climate zone here and pretty much north in latitude, you're kind of crazy not to look for some way, if you have the right site, to get the solar energy into your home, because it's free heat. And if you organize it and think it out right, it's a great resource. So that's what those two elements do for us. They give us heat. That's another view of the front. We have a little more heat we can gain on the second floor bedrooms there. So let me just leave that there and just briefly, I'm not sure I'm doing on time. I lost track here totally. So, okay, because I know we have time for questions, and obviously Monika has to present her project. So our house is built entirely with a SIP panel, which is this item right here. When you come up earlier, maybe you can see it. The SIP panel is a way of avoiding the thermal bridges that I mentioned earlier. It's like an Oreo cookie or a sandwich. So you have two layers of a engineered panel system, which is another green feature. It's better to use engineered lumber because it doesn't use whole trees. It uses parts of trees and leftover debris from lumbering. So this is called OSB, Oriented Strand Board. Two layers of that, held at the factory about 5.5 inches apart. They fill the void with a very high R value, fossil fuel sourced foam. So for those of you green geeks, you don't really want to use fossil fuel if you can avoid it, but one of the things that I was told by a experienced green scientist was, if you're going to use fossil fuel as a source for any of your products, make sure you use it really well. And that leads into the LEED system's requirement for durability of materials. So when you build something using fossil fuels as an element, you want to make sure it's going to be there for at least 100 years. So this fossil fuel derived foam here gives us extremely high R value for the walls, an R40. Now I can say that this is an R40 wall, truly R40, whereas most people will tell you that their wall is maybe R24, R30, but they got a regular stud system going. So you have to actually go in there and recalculate, because every stud, as I mentioned earlier, is losing heat. So the actual reading, the whole R value of a wall drops the more thermal bridges you have through it. This wall that we use in our house has no studs in it. It's just like the winter coat you put on when you go outdoors in the winter. You don't have a bunch of little sticks taking the heat off your skin and shooting it back outside again. So that's the main construction of the house. Then we put tar paper over that, because these manufacturers don't like the new building papers, they like tar paper. Then we put this thing on top of that, which provides a way to vent the siding. And that's another innovation in building science, where you don't just plaster your siding materials flat onto the wall of the building, you provide air behind it. So when you come up later, you can see, I've got an example of our Canadian Eastern White cedar shingles on these walls with this underneath, so that they can breathe. Any exterior cladding system will leak in some way. Cedar shingles are wood product, and they have all those joints, so a little water could work in from a windstorm, and as a result, you'll have dampness behind the shingles. Morning sun comes up, hits the shingles. Now you have the breadboard effect. Maybe you've seen that in your kitchen. Your breadboard was sitting on the counter in a little bit of water. It goes like this. It swells because the back is wet, top is dry. Same thing happens with a shingle. It swells on the back, the sun dries up the front, it cups. Now it can do that a few times, but once it's done it 4 or 5 times, a couple of years maybe, crack. And that's an example of durability of materials. Attention to durability is that you want to make sure then that you have this drying material, this space behind the siding, whatever kind of siding it is, so that it can dry on the back and the front. What else have we done here? Here's a sample of a sheathing system, with OSB skin, with a foam surface bonded to it. And this is what I talked about earlier about wrapping houses. So if you have a regular house, like many of you may live in a house built with studs, all you need to do, it's not such a little amount, but if you need to replace your siding, we just strip it off. We add foam to the outside of the house, just like a winter coat, all the way around. And then we reclad it with some method of venting the cladding. And now you have a hugely more efficient home with no loss to the interior space, but you've, had to go outside a little extra thick. This house here is a passive house done under the American passive house. So right now there's 2 passive houses, unfortunately. So the one that the Germans run is the one that Monika followed for her project. This one is using the Passive House America. I just want to briefly talk about it. So this one is existing because it's an old split level. So in this case, just like I was saying with that foam, we've actually added 6 inches outside the old studs, because to meet a passive house standard, as Monika well knows, it's the most rigorous energy model that you can follow, whether it's American or German. So in this case, I just wanted to show you this one because you don't have to have a house look modern, contemporary, whatever. I mean, energy efficiency can fit into any outward appearance. I think it's nice that our buildings look good because they're built well and their details look nicely assembled and they're thought out and their proportions are nice. And some people will say that's just all aesthetics. Well, I think it's really a blend. You need to find a way to have the building look good, because good-looking buildings people take better care of. And if they're built well, they're just going to last better. So that's a whole debate. But anyway, so here's an old split level. We chose to keep it. It's kind of insane, really. But it's 2,700 square feet with a small addition at the back. And this house will be absolutely zero energy cost. Now, later during the questions, we can talk about, payback and all that kind of stuff that you guys may want to talk about. But so this is a great example of what you can do with a single family if you have a willing client. In this case, this client is sort of a Sierra Club nut job, and they're willing to go a little extra mile to do something that a lot of us wouldn't think was worth it. They say, just tear it down. Well, tearing down is actually not a sustainable approach in most cases. Not all cases. There's some things you just got to tear them down. They're just junk. But in many cases, you can take an existing building, and that's really the future of America's energy efficiency in their buildings is going to be renovation work. Because we've got millions and millions of homes. A tiny, teeny fraction have been worked on like this, or Monika's house or my house. So, you have to realize that we're going to be renovating buildings going forward, and the ways of doing them that add efficiency to existing buildings is much more sustainable. Because think of it, I mean, you take a house down, the whole thing goes to the landfill. A lot of materials in there are totally worthwhile and usable. Even the foundation sometimes. Maybe sometimes we'll just take it down to the foundation and reuse that. So there's a lot to consider from that standpoint. Now, this is expensive to do because it's a one-family house. This is, we'll talk about cost later, but this is higher cost. If I go to do, say, a 30-unit multifamily passive house, I can do that at market construction cost because it's so efficient. So what happens is, as buildings get larger, you have an efficiency of scale. You have to worry less about heating because you've got so many units now packed in, sharing common walls. So you actually begin to be able to do things like the passive house, which is a very rigorous system of energy conservation. You can do it and meet the market construction costs. So the guys out there that say you can't do it, they don't know because they haven't tried it and they don't have the smarts to do it. But it's available. And so as we go forward, we're going to be able to both renovate and build new housing that is not going to cost everybody an arm and a leg. So I think I've probably said enough for the moment. We'll let Monika talk about her project, and then we'll take questions and talk about anything else that you guys may want to come up and ask about.
And I'm going to take it on the podium because
Okay.
I have a
Great. Okay.
Let me just get set up here. Oops. All right. Oh. Okay. Okay. I'm just gonna move this here so I have a little room. This is Chris. All right. All right. Hello, everybody. I became interested in sustainable architecture very early on in my career. When I was, after graduating school, I worked for a residential architect who was really adamant about using passive design techniques to build buildings. So we studied and we oriented all the buildings toward the south. We opened them up to let the solar heat in and provided thermal mass in the buildings to catch that heat. And at the same time, we studied how to shade it and provide brise-soleil for these buildings not to overheat during the summer. And at the same time, I was really getting interested in energy efficiency and building efficiently. And I think it was because at the time with my husband, we lived in an old colonial house that was very uncomfortable to live in, super drafty, cold in winter, hot in summer. And we were always dreaming about either renovating it or rebuilding it so it would be always comfortable to live in. And actually in 2012 we found a perfect candidate for such an endeavor, and it was a 1950s ranch, and its architecture was pretty nondescript, and it was very close to town, close to schools. And we decided that we would like to go ahead and actually start our renovation project and fulfill our dream. So we looked at several programs and standards that would sort of guide our renovation, and we looked at LEED that Chris was talking about. We looked at HERS. It's another rating system for energy efficient homes. But the program and the standard that really talked to us was Passive House Standard. And this standard is a very rigorous standard for energy efficient buildings. It's a performance standard, it's not a methodology, so it provides you with certain very rigorous energy demands that the designer must meet. And hold on, let me just, all right, and the numerical value for the Passive House Standard is as follows. So space heating energy demand cannot exceed 15 kilowatts per hour per year per square meter, and similar it's with the cooling. Primary energy demand, so all the domestic loads, hot water, lighting cannot exceed 120 kilowatt hours per year per square meter of usable space. And also the passive house buildings need to be very airtight, and the airtightness is checked by a blower door test, and the airtightness cannot exceed 0.6 air changes per hour at 50 Pascal pressure. So I wanted to put these numbers into perspective, so we sort of understand their impact. So I took some information from the 2009 residential energy consumption survey that shows that average New Jersey home that would be 2,399 square feet, and this translates to 223 square meters, would use, and I'll try to point, over 37,000 kilowatt hours per year, and 50% out of that energy consumption would be used for heating of such house. Comparing to the same size theoretical passive house, the passive house would only use 26,000 kilowatt hours per year, and for heating, it would only use 3,300 kilowatt hours. So the savings that you see here are significant. So actually, overall energy expenditure of the passive house, it's 30% less energy than the regular house, and when it comes to heating demand, it's 80 to 90% more efficient than the regular house. So when you think about that, it's really significant, because buildings produce 48% of greenhouse gases, and also they consume like 76% of total energy that power plant produce. And so widespread use of this standard would really produce significant energy conservation around the world. So to achieve these standard, there are certain measures that designers, architects do. Of course, they try to use passive measures like orienting the house toward the sun, shading the windows for the winter, for the summer season. But mostly, and also a very important feature is insulation. And all elements of passive house are well insulated. Walls, roofs, slabs, footings, and depending on a climate, in some climates, in milder climates, maybe 6 inches of insulation would be enough. But in more climates like Minnesota, that probably like 6 inches of insulation would be not enough. So, it probably would be like 16 inches of insulation that would be needed to build a house to passive house standards. Very important is what Chris was talking about, avoiding thermal bridges in the building. And it's advocated that passive house designers eliminate thermal bridging whatsoever, and this could be done by insulating buildings on the outside or avoiding penetrations, and sometimes using materials that don't conduct heat that easily. Also, Chris mentioned the fact that buildings need to be airtight to be efficient, and a passive house advocates providing airtight barrier that will not only prevent air from coming into the building, but also prevent or control water vapor entering the wall assemblies or roof assemblies to go in and to maybe condense in it. So so that airtight barrier and insulation need to be continuous around passive house buildings. The airtightness is verified by blower door tests, and the windows are super important for passive house, especially in cooler climates. So this is the value for the passive house windows in our climate, and this is the U value for passive house climate as per New Jersey, per our standard. So, and the lower the number, the better. So, all right. So when we wanted to do renovation, we looked into this standard to guide us, and we did not seek to get the passive house certification, but we used it as a guideline, that I said. So to remodel the 1950s ranch, we decided to do certain things that we could. We could not orient our building to the south because the south side faces our neighbor's driveway and garage. So, we didn't want to do that. But we consolidated mass. We actually got rid of the volume above the garage that was a bedroom and a bathroom, and added a second story to the building. And the first floor actually got opened up, so it's all one space, kitchen, dining, office, and family room. The second floor, it provides us with 3 small bedrooms and 2 bathrooms. And when we did a renovation, we knew that we cannot extend past the existing building outline. So with our thicker walls, we had to go into the usable living space. And this had to be actually a balance between thick walls and functionality of the space. So we were actually able to build double stud walls. So we used existing stud walls and provided an airspace in between the old stud wall and the new stud wall, and insulated that airspace with a continuous layer of rigid insulation. The roof over the new second story, it's very well insulated. It's an R60 roof. The roof over first story, it's R58 roofs. So the building has excellent thermal protection values, and it's airtight and very comfortable to live in. And here are some photos of taken during construction, and here I'm showing that exterior plywood was taped to prevent air getting into the house. This is the beginning of the double stud wall. Existing stud wall is there, and the window boxes are built in for the house. This is where the insulation arrived at the site. So the amount of insulation was really significant. This is putting siding on a building, and underneath the siding there is a layer, the layer that Chris was showing, that allows venting. And this is inside, putting insulation in and water and airtight barrier. The blue thing, it's an airtight barrier. More photos of that. Since the house is very airtight, the air, it's introduced to the house through a ERV, and the air is supplied to living spaces, and it's exhausted from service areas. And this is the ductwork for that purpose. The house also, it's outfitted with PV array, and here are a few photos of the finished product. Yeah. And also, here I'm showing our energy usage and energy production. So the green thing, it's a solar production. The purple bars show consumption. So we are running it almost at net zero. And here is, again, the comparison of our house and with the New Jersey average and the theoretical passive. So, in a typical New Jersey would use 37,000 kilowatt BTUs. Ours uses only over 11,000 kilowatt hours. So this is a significantly big difference. Also, when you look at the numbers at the bottom, so the 120, that was the number that it's required by passive house standard, and we use only 55 kilowatt hours per year per square meter of the house. So we are very proud of that. And that's it. Thank you.